Right now, the universe is expanding across the largest scales of space. The distances between distant galaxies are growing. The farther apart two unbound galaxies are, the faster that distance tends to increase. And yet, you are not expanding. Your hands are not slowly drifting apart. Your house is not becoming wider. Earth is not gradually losing its grip on the sun. Even the atoms inside your body remain almost exactly the same size. That should seem impossible. If space itself is expanding and everything exists inside space, then why is the expansion not stretching everything along with it? At first, the answer sounds simple. Gravity holds things together. But that is only part of the story. The deeper answer reveals one of the most misunderstood ideas in modern cosmology. Cosmic expansion is not a force pulling on every object. It is a change in the large-scale geometry of the universe. And once you understand that difference, the expanding universe stops looking like a giant explosion and begins to look far stranger. Most people imagine the Big Bang as an explosion. They picture all matter compressed into one point, followed by an enormous blast that launched galaxies outward into a dark, empty void. But that picture is misleading. The Big Bang was not an explosion that happened at one location inside an already existing space. It was an early state in which the universe was extremely hot and dense, followed by the expansion of the universe itself. There was no known central point from which every galaxy was thrown outward. And the universe does not need to be expanding into some larger emptiness beyond it. Instead, the distances between sufficiently separated regions of the universe increase with time. One common analogy is a loaf of raisin bread rising in an oven. Imagine that every raisin represents a galaxy. As the dough expands, the raisins become farther apart. A raisin does not need to crawl through the dough. The dough between the raisins increases in size. From the perspective of any raisin, the others appear to move away, and the farther away another raisin is, the more expanding dough lies between them, so the faster their separation grows. This resembles what astronomers observe on the largest cosmic scales. Distant galaxies generally show greater cosmological redshift, and the farther away they are, the faster their distance from us tends to increase. This relationship is known as the Hubble-Lemaitre law. But the raisin bread analogy creates an obvious problem. If the dough expands, why do the raisins not expand too? If cosmic distances are growing, why do galaxies, planets, buildings, people, molecules, and atoms remain almost unchanged? That is where the analogy reaches its limit. Cosmic expansion does not act like an invisible hand, grabbing every object and pulling equally hard on all of its parts. It is not a conventional force like gravity or electromagnetism. Instead, expansion describes how distances evolve in a large-scale model of the universe. That distinction matters because not every part of the universe behaves like the smooth cosmic average. The universe contains structure. Matter has gathered into galaxy clusters, galaxies, stars, planets, molecules, and living bodies. These structures have their own local physics. Their behavior is controlled by the interactions between their parts, not simply by the average expansion of the universe around them. So the question is not, is expansion pulling outward while gravity pulls inward? That picture is too simple. The better question is this system part of the large-scale cosmic flow? Or has it become a locally bound structure with its own dynamics? To understand the answer, begin with the Milky Way. The Milky Way contains hundreds of billions of stars, enormous clouds of gas, a central black hole, and a vast halo of dark matter. These components are not randomly drifting beside one another. They form a gravitationally bound system. Stars orbit through the galaxy's gravitational field. Gas clouds collapse and form new stars. Some objects move inward. Others are thrown outward. The Milky Way changes constantly, but it does not simply scale up as the universe expands. Its internal motion is controlled by local gravity. This is why the stars in our galaxy do not join. The general Hubble flow and drift steadily away from one another. People often say that gravity is stronger than cosmic expansion. That statement is useful, but it can also create the wrong image. It sounds as if expansion were a pulling force, trying to tear the galaxy apart, while gravity fought against it. In reality, the Milky Way is a local gravitational system whose internal geometry and motion are different from the smooth, expanding model used to describe the universe on enormous scales. A galaxy exists inside an expanding universe, but it does not expand in the same way as the distances between distant, unbound galaxies. Andromeda gives us a clear example. Although the universe is expanding overall, the Andromeda galaxy is moving toward the Milky Way. The two galaxies belong to the same gravitational neighborhood. Their local gravitational attraction dominates their motion. This tells us something important. Cosmic expansion is not a universal conveyor belt forcing every galaxy away from every other galaxy. On sufficiently large scales, expansion dominates. Inside locally bound systems, local physics dominates. Now reduce the scale. Earth orbits the Sun at an average distance of about 93 million miles. If Earth and the Sun behave like two distant, unbound galaxies, the expanding universe might appear to increase the distance between them, but they do not behave that way. The solar system is gravitationally bound. Earth is not a free particle drifting with the Hubble flow. It is moving through a stable orbit, determined mainly by the Sun's gravity and Earth's existing motion. The influence of cosmic expansion on planetary motion is extraordinarily small compared with the forces governing the solar system. That is why Earth does not slowly spiral away, because the universe is expanding. The same is true of the Moon. The Moon is gradually moving away from Earth, but not because space is stretching between them. Its recession is mainly caused by tidal interactions. Earth's rotation transfers energy to the Moon's orbit, slowly increasing the distance between them. That motion is real, but it is local physics, not cosmic expansion. This distinction is essential. Not every increasing distance is evidence of the expanding universe. The cause depends on the system. Galaxies can separate because of cosmic expansion. The Moon can recede because of tides. A spacecraft can move away because of momentum. The universe does not use one explanation for every kind of motion. Gravity explains why galaxies and solar systems remain together. But gravity is not the main force holding your body. At a fixed size, at the scale of atoms, molecules, cells, and living tissue, electromagnetism and quantum mechanics dominate. Electrons are bound to atomic nuclei. Atoms form molecules. Molecules form proteins, cells, bones, muscles, and organs. These structures have stable arrangements and preferred sizes determined by local physical laws. Your body is not a loose cloud of particles, freely following the expansion of the universe. It is an organized system of electromagnetic and chemical bonds. This is why you cannot take the Hubble expansion rate, multiply it by your height, and conclude that you become slightly taller every day. That calculation would treat your head and your feet as though they were distant galaxies, moving independently with the cosmic flow. They are not. They are parts of one connected physical structure. Your atoms are not secretly growing at an undetectable rate because the universe is expanding. Their size is governed by quantum energy levels, electromagnetic attraction, and the properties of fundamental particles. The same principle applies to your phone, your house, a mountain, or the entire Earth. These objects do not simply scale up with the cosmos. They are built from matter, whose parts are locally bound together. The universe is expanding. But your body is not a miniature version of the universe. This leads to a difficult question. If your body does not expand, Earth does not expand, the solar system does not expand, and the Milky Way does not expand, where does cosmic expansion actually begin? There is no sharp boundary. There is no invisible line where gravity suddenly switches off and expansion switches on. Instead, the answer depends on scale, density, motion, and whether a system is gravitationally bound. Inside planets, solar systems, galaxies, and many galaxy groups, local interactions determine how matter moves. But when we step back far enough, the universe becomes more uniform on average. At those enormous distances, the overall expansion becomes the more useful description. Two atoms inside your hand cannot be treated like distant galaxies. Two planets orbiting the same star cannot be treated like unbound regions of the universe. But two distant galaxy systems, separated by vast amounts of space and not held together by gravity, can move farther apart as the universe evolves. Cosmic expansion becomes visible only when we observe the universe at the correct scale. A person is too small. A planet is too small. A solar system is too locally organized. Even a galaxy is dominated by its own internal structure. Only across the enormous distances between unbound cosmic systems does expansion reveal its full effect. This is why the universe can grow without making every ruler longer. Our measuring devices remain locally stable, while large-scale cosmic distances change. That is also why expansion can be detected. Light traveling across the expanding universe has its wavelength stretched, producing cosmological redshift. By measuring that redshift and comparing it with distance, astronomers can reconstruct how the universe has changed over billions of years. The story becomes even stranger. For much of the 20th century, scientists expected gravity to gradually slow the expansion of the universe. Matter attracts matter. So it seemed reasonable that the expansion should lose speed over time. But observations of distant supernova revealed something unexpected. The expansion is accelerating. Something appears to be causing the large-scale universe to expand faster with time. We call it dark energy. The name sounds like an explanation. It is not. Dark energy is a label for whatever is driving the observed acceleration. It may be a constant property of empty space. It may be a field that changes over time. Or our understanding of gravity on cosmic scales may be incomplete. We know what dark energy appears to do. We do not yet know what it is. At the moment, it does not tear apart galaxies, planets, atoms, or people. Its influence becomes significant across enormous cosmic distances. But there is a hypothetical future in which that could change. Under the standard cosmological picture, dark energy behaves like a cosmological constant. In that case, the universe can continue expanding forever, while gravitationally and electromagnetically bound systems remain intact. Distant regions would become increasingly isolated. The universe would grow colder and darker. But atoms, planets, and galaxies would not necessarily be torn apart. However, some speculative models suggest a different possibility. If dark energy were a form of phantom, energy whose density increased over time, its influence could eventually become strong enough to disrupt even bound systems. Galaxies could lose their structure. Planetary orbits could fail. And near the final moment, matter itself could be torn apart. This hypothetical ending is known as the Big Rip. But the Big Rip is not the confirmed future of the universe. It requires dark energy to possess very specific properties that observations have not established. Dark energy may remain constant. It may evolve in another way. Or our current theories may still be missing something fundamental. The frightening part of the Big Rip is not that we know it will happen. It is that the equations allow it to happen under the right conditions. Cosmic expansion, which currently matters mainly across the greatest distances, could one day reach down into the smallest structures. But for now, that remains a possibility, not a prediction. So why is the universe expanding while you remain the same size? Because cosmic expansion does not mean every object is being physically stretched. It describes how large-scale distances evolve across the universe. Galaxies, solar systems, planets, atoms, and living bodies are local structures. Their sizes and motions are governed by gravity, electromagnetism, quantum mechanics, chemistry, and the relationships between their parts. You are not protected from expansion by an invisible shield. You are not standing outside the laws of cosmology. And Earth does not occupy a special place. You simply do not belong to the Hubble flow. You are part of matter that has organized itself into a locally bound structure inside an expanding universe. The distances between remote cosmic systems can grow. But inside those systems, matter follows a different story. Stars remain inside galaxies. Planets remain in orbit. Atoms hold their electrons. And for a brief moment in cosmic history, those atoms have arranged themselves into something capable of looking into the darkness and asking why it is not being pulled apart. The universe is expanding. You are not. And the reason is not that you are an exception to the universe. It is that you are one of the structures the universe has built strongly enough to hold itself together. What do you find more unsettling? That the universe is expanding into a colder and more isolated future, or that dark energy could be capable of something as extreme as the Big Rip? Share your thoughts in the comments. And subscribe to Cosmic Theory Lab as we continue exploring the hidden forces, impossible questions, and possible futures of our universe.